So now let's take a look at this idea of conjugate acid-base pairings. Now I'll probably provide some examples in a separate video of how one goes about solving conjugate acid-base pairs, but you should understand a few kind of key points about them. Alright, first, in any equilibrium drawing reaction where we're talking about there being a reaction that's happening on the left and then something on the right, you have an acid and base. Now on the left, it's called an acid or a base depending on its behavior, and on the right, it's termed a conjugate, which means kind of on the opposite side of it. You always have your basic or your acid and base on the left, and then its respective conjugate acid or conjugate base pair on the right. Now, without practice, if we're looking just at the general scheme of this reaction, they've drawn two lines connecting each side, where you have a line of a base connected to an acid on the right, and you have an acid on the left connected with the base on the right. And what that line is drawn there to show is it's showing you that these guys are kind of partners in crime, where if a compound behaves as an acid on the left, it's going to operate as a base on the product side or the right side. And conversely, if it acts as a base on the left, it's going to behave like an acid on the right. And so to reinforce this concept, there are practice problems that I'll kind of look at, but I want you to be aware that the behavior of them is that they have kind of the opposite effect from left to right. Adding to that, and then you probably see this in the presentation, is that if something behaves as a strong acid or strong base, they tend to behave as a weaker version of themselves on the opposite end. So imagine if you have a strong base on the left, which is highlighted in the blue. If you look at the right, where it has what's called its acid, conjugate acid, that conjugate acid would in fact be weak. So they reciprocate their roles in opposite form, where one is strong, the other is weak, where one's weak, the other is strong. And so that's kind of their behavior, and you'll notice that once you kind of get in the habit of like being able to identify them. But to me, the biggest way of identifying them is trying to look for that proton and where that proton is moving, meaning that H group. And that's going to be vital. Now, as I mentioned before, what dictates whether something is a strong or weak acid or base is its ability to easily break off and that proton be donated. That means to completely dissociate. What I'm talking about, that I'm saying its ability to go from being HCl to becoming something else. And so when it's strong, you have 100% success rate where that H breaks off. However, when you're dealing with weak acids, you tend to have a scenario where that dissociation does not happen as strongly and not as pronounced. Concurrently, when you think about the behavior of bases, because they tend to accept protons, their propensity or tendency to accept is based on their ability of being weak or strong. If they're weak, they have less affinity for a proton, and when they're strong, they're willing to go out and react and interact with these new H groups that are formed from the dissociation of an acid. Now, this diagram just further corroborates what I was saying prior, where if you have an acid and it's regarded as strong, its conjugate or reciprocal base or conjugate base will behave weaker. And so if you look on the left, where you might see at the top it says perchloric acid, if you look on the right, it has perchlorate ion. Now, the perchloric acid is a really, really, really strong acid. And when it reacts, it forms a reaction, and then on the product side or the right side of that reaction, it'll end up yielding a perchlorate ion that is substantially weak as a base. So its conjugate, so it would perform as a strong acid, and then its conjugate would be a weak. And so this just shows that reciprocal tendency of whether it's strong on one side, it becomes weak on the opposite end. Now, we mentioned monoprotic, we mentioned diprotic, we mentioned triprotic. Whenever you have more than one H group, it's always willing to give up that first H group, but not as willing to give up any of the other ones if it has more than one. And so they actually can assign a value to that, but when you have something that's strong, it tends to completely dissociate, up to 100% when it has those extra H groups to give up. And so again, recapping what I said about strength of an acid and its conjugate, if it's strong on one side, it's weak as a conjugate base on the opposite end, and that affects their behavior as acids and bases. But please understand there is always an acid and a base on both the left and right hand side. However, you have to be more specific when you're looking at one side of the reaction, which is usually the right, because that performs as the conjugate acid and conjugate base. Now, when we're looking at acids, one of the things they use to measure acids is pH, and pH ranges from 0 to 14. Now, if a compound has a pH that's less than 7, it is acidic. If it is right at 7, it is neutral, and if it's above 7, it is basic. And the equation that's provided on this document just highlights the relationship between measuring the proton donor protons and the actual pH value. Reiterating that, this diagram just kind of says the same thing, where if you know your pH value, you can determine whether it's acidic, basic, or neutral. Concurrently, if you really wanted to look into it, and I don't challenge anyone at this point, but if you're interested, if you know your concentration of a compound, then you can go ahead and identify it probably as acidic, or basic, or neutral if you know how much of its respective hydronium, hydrogen ions are present. Equally, there is a relationship between pH and a term called pOH, and pOH refers to the measurement of not the hydrogen ions, but your hydroxide ions, and that's used to measure the basicness of a compound, if you will. Now, the sum total of both of them yields a value of 14. So equally, if you know your pH value of 14, you can deduce the value of your other one by simply subtracting from 14. Now, if you're talking about doing the math for going for pH, sometimes you're going to have to be familiar with inverse log, and that's when I call people to be really familiar with their calculators and have a level of comfort knowing how to manipulate them. And while there's not a lot that I'm covering about buffers, I did want to make you aware of how a buffer system works. When it comes down to buffers, there are many biological systems that rely heavily on buffers, to maintain homeostasis or continuity or just overall well-being. One of those buffer systems is in our blood. Another one could probably be regarded in our stomach. But the way it works is a buffer system is basically a solution system where when you have a certain pH range you're looking to keep something in, you have this system where if you introduce an acid, it does a reaction, or a reaction occurs to offset the impact of adding that acid, or the system does something to offset the addition of something that is basic. Now, in both cases, they have a threshold, but it has a buffer system that's in place to keep things in a certain range. One of the examples, and I think I'll talk about it a little bit later, is with your blood. When you have to maintain your pH in your blood, if it gets beyond, 7.4 and it gets too high or too low, that can cause severe biological trauma. And so the body has certain things in place to help offset the effect of introducing components that may be too acidic or basic. And so, this talks about the buffered systems in the body. And like I said, it's just a cool thing to know about because buffers help maintain the status quo of a healthy body. And like I said, the range for normal blood ranges between 7.35 and 7.45. And if you introduce too much acid, it will overcome that buffered system and that would cause severe bad conditions, which are listed here in the slide, acidosis and alkalosis. Now, in terms of molarity, we've already explored that concept. Normality probably won't be explored in this particular unit, but the molarity is usually the concentration that we're using when we're talking about doing pH calculations. So you'll want to be familiar with that terminology of molarity. Now, I don't know if you know this, but in acids tend to feature these things called carbonates that are used to neutralize excess stomach acid. So if you ever notice when your stomach becomes upset or discomfort, maybe you just ate a bunch of hot wings, that's because the natural pH of your stomach has been disrupted. And so it helps to have things like antacid, or if you ever think of milk, which tends to be higher on pH, like closer to like 7, 8 in pH value, it tends to help out with an upset stomach. Now, to reiterate, like I said, we talked about various solutions. We have our acidic compounds, our basic compounds, and there are plenty of examples of behaviors of those compounds. Likewise, there are things that can be used to create buffered systems, and there's a specific paradigm for what you need in order to create that compound. Now, as far as the presentation goes, that pretty much culminates everything we needed to talk about. The huge emphasis, of course, is going to be on acids and bases. And so all of the featured conversations that were talked about as it relates to acid and base is what you're going to want to focus on.